Well, good afternoon. It's a great pleasure to see everyone here in person after a 3-year hiatus. So what we decided to do this year, and what you're going to see, is more of a very future visionary look at where we see overall software and automation technology going. And then we talk about boundless automation really in 3 pieces: the intelligent field, the cloud, and the edge. So we will start with an overview, go through each of those 3 areas, and then I'll come up, do a little summary. So without any further ado, we should get started. Let's look back at what some of the past inflections have been. Maybe a big one was when we first came out with microprocessors in the intelligent field. Then there was the transformation to off-the-shelf technology, Wintel, Ethernet. Emerson had a big role in that, led the industry in that area. Then in the last 10 years or so, I'd say, big push to move the field into being more distributed and move the field out into the field with distributed I/O and other kinds of field-based connections, taking them out of the control room and into the field. Another area where we feel very proud that we pioneered that with our electronic marshalling with CHARMs. So before we talk about what we see the future looking like, let's talk a little bit about what the present looks like, and what are maybe some of the good points of the present, but also what are some of the limitations of today's automation architectures that we see. For years, we've always talked about the Purdue model and layers of automation. It really is more about the organization of a manufacturing company and what needs to pass from each layer to the next inside of manufacturing. But one of the most common expressions in the software world is that architecture follows organization. And so what we've seen happen, again, starting in the 90s, is we've seen things transform to where we typically have a layer of automation networking, a layer of software applications that corresponds to the relative function inside of the plant. That's also led to kind of a very hard segmentation in the past between operational technology and information technology, or OT and IT as we call it. And I always joke, for a long time, for the OT folks that we would talk to, it felt like they would talk about IT as, here's your data, now go away, leave us alone. You know, you don't have the same kind of uptime considerations we have, you don't think about, reliability the way you do, here's your data, go feed that into your ERP. That's not going to work, as we, I think, all now realize as we go forward in the world of digital transformation. But those layers of automation architecture, like you see here, like we always talk about them, has also set up a security structure where we kind of count on these layers to be our security hierarchy, where we protect the lower layers that are the most critical by providing firewalls and other layers of security on top of them in the upper layers. And that whole architecture is kind of really designed to be kind of a one-way up architecture. We always think of the data flowing from where? From the bottom to the top, right? From the sensors to the boardroom, as the old expression used to go. So that actually restricts some of the data flow, and it prevents a lot of valuable information from easily moving up through the layers and getting it to where you want it to be. And as we've looked at digital transformation applications, a lot of times we want sensor data, for instance, to go directly to the cloud. And that's become a challenge because most people are used to thinking of how they work sensor data up through this hierarchical architecture. That architecture has largely been focused around automation. So things like control, safety. When we think of that architecture and the types of data it's designed to bring and the types of applications, it tends to be around automation of the production process itself. So then you find other vertical silos of data and software applications in other operational domains inside of the plant. So you'll find a vertical silo of reliability data, you'll find a vertical silo of quality data, and increasingly you'll find a vertical silo of sustainability and energy consumption kind of data. It works. We've been able to provide some layers of security, although the security gets complex as you look at setting up these layers and the configuration of firewalls. And today, when we actually want to bring all this data up into the cloud, or we want to have universal visibility of it, the traditional solution is to layer yet another set of data model and data aggregation on top of it that we call the OT data lake. That's a way to do it. That's the way to make sense out of what exists in plants today, which are these fragmented, both vertical and horizontal silos of different kinds of data, each built around their own architecture and, more importantly, their own data model. So we've had to layer another set of software on top of that in order to produce a consistent context that then makes it able to be ingested and used effectively when mingled with production data, enterprise-level production data in the cloud. There's a better way to structure software and architecture going forward to solve this issue of both enabling the easy movement of data across various functions and applications inside a facility or across an enterprise, as well as being able to look at different domains, again, sustainability, reliability, automation, and have a more encompassing data model to bring all that data together inherently where it's generated or in the systems that inherently produce it, so that you don't have to worry about doing that later in something like an OT data lake. So the way we see the future and the paradigm and the way we talk about it and like to describe it is not these hierarchical layers or these vertical silos of applications, but really three parallel, or I should say peer computing domains, the intelligent field, the edge, and the cloud, that are tied together through a cohesive software platform, so that software running in any one of these domains, any one of these computing domains, is able to seamlessly interconnect and blend the data between all three of them together into a holistic data model, which is a key part of what we see as this cohesive software platform. If we look a little more closely, what do we mean by intelligent field, edge, cloud? Well, the intelligent field is really the outgrowth of that very first paradigm change where we first pioneered the idea of intelligent field devices. But what's happened is intelligent field devices, and especially as you look at new technology coming like APL, are continuing to add more horsepower and are becoming, frankly, more like edge devices themselves, with the ability to actually run software workloads and applications inside the devices themselves. But when we use the term, what we still mean are devices that are physically connected to assets, right? And typically are either got sensors in them, collecting data from that physical asset, or maybe you're actually taking an action on that physical asset, like a control valve and its digital valve controller. The edge is a term that's probably the newest of all these three terms, meaning that it's right there where the data is being generated, where that data hasn't traversed over the public internet. So local computing, typically down close to where the actual data is being generated, in comparison to the cloud, where we're actually looking at remote computing resources. But the cloud is a lot more than that, as you'll see when we talk further. Cloud has become something that's really transformed the way software is written, designed, and deployed. And that's one of the key technology changes we're going to talk about, is seeing those technology changes coming down into the automation world. Underpinning all of that still, in order to make these things work together in an easy-to-use manner, is a cohesive software environment. What do we mean by that? There's a lot of focus and a lot of talk around connectivity between software and applications, and a lot of talk about protocols. But I think one of the things that people who have worked digital transformation programs have learned is that connectivity is far from enough. Connectivity just gives you access to the data. It doesn't tell you what it means. It doesn't give you context. And frequently you find the same thing referred to 4 different ways when it's used in 4 different domains, whether it's in automation, where it might have a tag name, in reliability, where it may have an actual asset name inside of a CMMS, or in safety or a lab system where, again, may have a whole different context and name, because those have been set up specifically for the domain and the application that they work in. What you really want is to not spend the time layering yet another data model or working to bring these together in a common data model so you can talk to them. You would like them to inherently be able to generate that from the beginning. You want what we call integrated by design. Integrated by design is a concept I know everyone in this room has used and appreciates, because it goes kind of all the way back to Microsoft and the Office suite. And the idea that here's 3 separate applications, but data model, whether it's a little chart or an object or a picture, the consistency of that and what you can do with it is going to be shared across all 3 of those applications, and you're going to be able to move things seamlessly back and forth between those 3 applications. That was probably the first big example that everybody can think of, but since then, many successful software ecosystems are built around this concept of an integrated data model. What won was integrated data suites from 2 big companies. Oracle and SAP became the dominant market share because people realized trying to tie these different data models together was very difficult. The number one thing that delivers for you is ease of use as an end user. The most famous one in the consumer world is Apple's ecosystem. So if anybody has proven that having integrated data model and an integrated ecosystem for all their different software pieces is something people appreciate and are willing to pay for, I think Apple is probably the biggest example in our recent history. It also provides that data democratization that I talked about earlier, because that context is now a shared common one, independent of where that data came from, so you know how to use it. The meaning of the data is consistent from software to software, enabling much easier utilization of that data in applications. Having an integrated suite of software also enables you to provide solution-level security, not just at a component level, but today what people want in automation is things like ISA Secure, which is a solution-level certification across an integrated suite of applications. Now, what about standards? Well, standards have an important role to play. Standards, frankly, are always going to provide lowest common denominator level of integration and shared data model between application and software from different vendors. That's going to provide interoperability. But if you want extensibility of the integrated data model, you have to do what some of those other vendors I just talked about and have published APIs as to how other players in the marketplace can actually integrate into your overall integrated suite of software. So this cohesive software platform or cohesive data model is a big central theme what we're going to talk about today. But for now, what we'd like to move to is let's talk about the role that the intelligent field has to play. And for that, I have my friend and colleague, Laura Schaefer, to come up and talk to you.
Thank you, Peter. Hi, everybody. My name is Laura Schaefer, and I'm the Vice President and General Manager of Pervasive Sensing and Connectivity. For those of you who may not know, Pervasive Sensing is our group that adapts wireless technology into our Rosemont sensors. Now, just over a year ago, we added connectivity to my title as we see the importance of accelerating the development and adoption of new connectivity technologies across our instrumentation portfolio. So I'm really pleased that my team is working on Ethernet APL, we're working on cellular, we're working on a lot of those technologies that are going to enable us to connect our data into this boundless automation of the future. So when you sum it up, what is the intelligent field's contribution to the vision of boundless automation? Well, it's more democratized data. More data from more sensors, and more data from those devices that are stuck down below that first firewall that Peter talked about. Rich data sets that are just criminally underused. We want to unlock all of that with the intelligent field. So before I launch into how we're going to unlock that data, let me first talk about the different connectivity options that are out there and which ones we see as important for the future of boundless automation. So I'll start with wireless. I think wireless is going to continue to be a very important vehicle for enabling more devices to be adopted by our customers. We developed Wireless HART with the FieldComm group back in the 2000s, And we developed it really with the process industry in mind. We adapted our existing devices and put wireless in them. But we've seen wireless HART get adopted into distributed assets, and we've seen it adopted into discrete and hybrid manufacturing as they have additional objectives around sustainability. So wireless HART we see is continuing to be important. But additionally around wireless, we see the rise of 5G. So of course, you use 5G on your phones, et cetera, but we're going to see that continue to move into the process in discrete and hybrid manufacturing spaces. And we've heard a lot about customers starting to stand up their own cell towers and start to examine how they could use 5G to bring more data back to their stakeholders. The last connectivity type that I want to call to attention in the realm of boundless automation is Ethernet. Ethernet's seen a lot of adoption in discrete and hybrid manufacturing, but it's really stopped when it comes to process because Ethernet hasn't been suitable for our hazardous environments. With Ethernet APL, we're going to unlock Ethernet, high bandwidth data, for our process environments, allowing more of that data that is currently locked under the firewall, allowing that data to flow to the surface and be used by the stakeholders who want it. So those are the connectivity options we have. Let's talk first about how we're going to deliver more devices into the field to suit the stakeholders, like our reliability colleagues who need a lot more data than they currently have. We see wireless as the ideal vehicle for that. Wireless allows you to drop in data where it's required. And for boundless automation, we see two specific scenarios that we are very interested in making sure that we're addressing as we move to the future. One is stationary high-density IIoT. We've got a lot of sites with hundreds, thousands of devices. But as we look to a future where customers are saying they might need 8 or 10-fold more times measurements, that's a lot more wireless that you're packing into a small space. And we need to make sure that that's reliable, and we need to make sure that that is at an ROI that makes sense for what a customer is trying to achieve. So how do we do that? Well, at Emerson, we still see wireless HART as the ideal vehicle for communication device to device. So in a hazardous area environment, you're making use of wireless HART's superior reliability, its low battery usage, so much longer life for a single battery, and wireless HART allows you to address that device. So if there's ever an issue, you can reach out, ping that device, and get a response immediately. Other wireless protocols don't allow you to do that. You're waiting maybe an hour or more to hear back from that device. So wireless HART is still preferred in the hazardous area. What we need to change is how we backhaul that data. We need to take in hundreds and thousands more devices through a single access point and stream that high bandwidth data back to the folks who need it. And we're going to do that by enabling our access points with Ethernet APL, pulling back a significant amount of data there in hazardous areas, and also offering the same with 5G. You have all the data being transmitted with wireless HART on site in the hazardous area. It's aggregated at those access points and sent back with your high bandwidth technologies. The devices themselves will evolve as well, and we've already started that journey. So here is the AMS wireless vibration monitor. This was launched since the last exchange, a matter of fact. And you'll see what's different with this device versus some of our traditional devices that we've come out with is that it's small, compact, very light. This is an engineered polymer cover. It has no LOI. Right? It transmits all the data to the edge or to the cloud wherever that data needs to be consumed. And we're going to see more devices like this moving forward as we bring affordable devices to customers for broad adoption for reliability, quality measurements, et cetera. The second scenario that we see for the future is mobile single assets. And this is where 5G comes into play. As our supply chains or our inventory managers want more data, we'll look to enable 5G in some of our traditional measurements. So leveraging technology that was developed by our cold chain division within Emerson for monitoring temperature in food containers as they're transported across the globe. We're going to leverage that into some of our traditional process measurements. How do we unlock the measurement that is below the firewall? Well, this is where Ethernet APL comes into play. Ethernet APL offers significantly more bandwidth, more power, all in intrinsically safe areas. And we're really excited to begin working on this and look to how we can accelerate adopting this across our measurement devices. This is going to unlock a lot of information for our customer that perhaps they're not using effectively today. Particularly when you look at our data-rich devices like a Coriolis meter, a flow meter, or like a non-contracting radar level device, there are rich data sets in there that are really not being used today. We've got waveforms that tell us where interfaces are. We've got apps that sit on the transmitter that give us insight into multi-phase flow or concentration measurement. All of this is stuck effectively when it comes to being below a firewall. Ethernet APL will allow us to stream this at high resolution to allow customers to make use of it, whether that be at control, on the edge, or in the cloud. One of the barriers to adopting a new protocol or new physical layer like Ethernet APL is just that migration path. And we're really pleased to demo our new APL switch. So with the new APL switch, that is giving us an APL charm that allows you to drop an APL device next to your legacy devices, allowing you to try APL or start putting APL in where it makes sense for your application without a rip and replace strategy that would otherwise be required. This is fully redundant on the backhaul, and it enables us to go straight from the devices through the switch to where that data needs to be consumed, whether that be on the edge or the cloud. So now we've talked about wireless, we've talked about the future wired. Let's talk about how all of that data now gets resolved up in the cloud. Peter talked about the challenges with having all the data in the same format, and that is definitely a challenge that has prevented some of our customers from realizing their digital transformation. To help us along the way, we have got the PADIM Unified Data Model. And this is a data model. We are very involved in the standards committees that support this. There are currently 8 standards committees that are endorsing and adopting this unified data model. And we see a future where each of our devices is going to have some way to communicate in this data model. So PADIM stands for Process Automation Device Information Model, and it's a standardized way, regardless of the protocol, for a device to communicate what it is, what it's telling you, who it's from, etc. And it's a very unified way. If all the data comes to the cloud in this format, it makes use of that data significantly easier. So what we see here is that our devices that will connect directly to the edge or directly to the cloud, like right here we see tank level, we see pH level, we see those will communicate directly either via MQTT or OPC-UA with the PADIM model on top. For our traditional devices like temperature, pressure, etc., that might be on a DCS, those will communicate up through an FDI data server, and that FDI data server will translate those traditional protocols into either MQTT or OPC-UA, again, with the PADIM model represented to make sure all of this data flows through appropriately. Now, really pleased to share that our AMS Device Manager is the very first FDI host to be certified by the FieldComm group as an FDI server. So we've already got the building blocks in place to realize this vision. I'd like to share with you 2 applications showing how Emerson is helping the customer get better insight from their data, where, both on the edge and in the cloud. First, our valve condition monitoring group has been doing this for a while, but we're going to continue to evolve this. They are streaming data from their digital valve controller, and they're streaming that data via HART into an edge device From this edge device, they are taking via cellular up to the cloud, the Emerson cloud, where we analyze this data with our professionals, our valve experts. And they provide information back to the customer on how their valves are doing, helping them understand when they need maintenance, how critical that is, and when to expect to need to do that maintenance. Coming in 2023 or early 2024, we're going to have a PlantWeb Insight app for the valve health that allows that customer to have that additional insight on the edge so they get their own first pass on valve health without waiting for the analyst to get back to them. We've had this in place for a bit, and we've had customers report back that this has been very successful for them. We've got customers reporting 0 unplanned downtime for critical valves, 50% less on major maintenance event costs. Compressed air optimization is a new app for us. This is making use of the Aventix AF2 flow sensor. They're measuring compressed air here. So compressed air is a major expense for some of our manufacturing customers. By measuring it real time, they're able to detect leaks, and they're able to actually control as well. So if they see a major leak event, they can shut off that compressed air flow and make sure that you're not wasting a ton of compressed air, which is ultimately a lot of money and energy as well. So with this, they're streaming that data via OPC UA and MQTT, analyzing that with software that's either installed at the customer's edge or it can be installed in the cloud. This is saving our customers an average of $80K per year on average maintenance costs, and it's resulting in 20 to 30% less compressed air consumption. So we're really pleased to show these examples. We've got 13 different PlantWeb Insight apps that are all out there to help customers analyze their data at the edge and provide that next level insight for their data. So with that, I've showed you how we get our data, how we're going to democratize that data, make sure it's all in the same format. I'm going to hand it back over to Peter to tell us what we're going to do with it all once it's in the cloud.
Okay, well, so obviously cloud has, I've used the term here, conquered IT. If you've talked to any of your IT professionals in your company, you know that that's where they're headed. If they're not moving their stuff to the cloud today, they're planning to do it tomorrow. Why has that not happened in OT? Well, I can tell you 5 or 6 years ago, when we would have a crowd of OT people come and visit us and you would talk about cloud, they'd get this horrified look on their face and think of security and somebody else having their data. That skepticism, I would say, has rapidly been declining, largely driven because of digital transformation programs, in my opinion, which has pushed IT and OT to collaborate together more. And of course, the IT folks are looking at the cloud as the place with the horsepower and the data aggregation capability to do bigger and broader applications. The whole market around looking at streaming data from sensors has gone from being something that only we manufacturers care about to something that many, many industries care about. And in fact, you know, the amount of data that can come off of a car right now can exceed or equal the amount that can come off of a small manufacturing plant. So this has become a market where it's big enough for the cloud guys themselves to be interested, and so they've started to add their own native services and their own native applications in their cloud environments to ingest that data and to also provide some of the data visualization, analytics, and displays, things like Power BI, for instance, of that data in a domain-independent way. So when you start talking about applications that are very domain-dependent and require knowledge about the area, that's going to stay the realm of companies like ourselves. But when you talk about some of the generic data ingestion and visualization, the cloud guys are actually now a new competitor, frankly, for many of us in that space in terms of being data ingesters and visualizers. Now, what is it that everybody loves about the cloud? Well, the vendor, the cloud provider themselves takes on the infrastructure. There's no software on clients. It's universally accessed. We all love that as we look at our stuff on our phone or our tablet or our computer, and it's all the same stuff. It has elastic scalability. It can be very small, it can be very large, and you only pay for what you use with that scalability. All those are benefits why IT has loved cloud and why OT is going to love cloud as well. Now, some of the things, though, that are going to be benefits when we start applying cloud to OT that are unique is if we have multiple facilities using that same unified data model, it becomes aggregating that data at an enterprise level in the cloud very easy, and it enables an enterprise level look and compare and contrast across an entire enterprise instead of just a single plant. Bringing the data to the cloud allows integration with enterprise data that's already from ERP and other functions that's already in the cloud. That gives you business level optimization, not just production and OT optimization. Having data centralized in the cloud enables experts anywhere in the world to be looking at that data and providing advice, again, anywhere in the world to an operating facility, either from in-house experts or external experts like the valve monitoring that Laura just told you about. And if you have that enterprise level look in the cloud, then you fundamentally have built-in operational redundancy, because with the cloud, people can log in from literally anywhere and take over if it's needed for a period of time, or assist operations at another facility, again, could be anywhere in the world. The other thing that cloud brings that is, not an operational perspective, but is certainly, or operational benefit, I should say, but is certainly an important one, is a whole new paradigm for support. Okay, so if you think about the specification, the acquisition, the configuration and deployment, and then the support of products, cloud opens that wide open for digital online assisted methods. And in our case, we see all this happening through myemerson.com. There's a number of different sessions happening in the Exchange. You're going to see some of this in place. We have a big vision here. We're a ways down the track, but the final vision is, of course, you have all your preferences built in. You could configure any of our devices. As you install them, if you're able to set up that cloud connection like Laura talked about, and if we're allowed to actually, from a privacy point of view, have some visibility of the device, we can auto-generate an entire installed asset database for you of what you have. And alerts can be something that we automatically pick up and tell you, hey, this is something you need to do maintenance on, or we can tell you what spare part you need ahead of time. It's a whole new support model. Now, perhaps one of the biggest reasons, though, that we talk about cloud here, we want to bring out cloud. Cloud has become the new way to develop software and deploy software and administer and maintain it. One of the key technologies is containers. So, in my over 30 years of software development, I've watched people try to modularize software in different ways and make software shareable. And at first in the 90s, it was objects. Okay, we're going to have all these object libraries and that can be reused. Well, they were kind of too small and were dependent on which operating system you're on, a lot of other things. Then we had virtualization, where you took the whole machine full of software and said, okay, I'm going to run that wherever I want. Well, if I were to say that objects were too small and virtual machines were too big, containers are the Goldilocks of software modularization. They're just right. The concept of having a set of services with the required functions and files that are needed for those services and security wrapped around that particular modularization container that holds that, that's become a mainstay of how cloud software is written and deployed. And it provides a level of modularity because you can increase scale easily by replicating containers. Containers can live anywhere in that edge cloud field architecture we're talking about and still communicate seamlessly with each other. So they're inherently fit this distributable software model that we're talking about. The other thing that comes with the cloud is fleet management. So here in automation, we can learn a lot from the cloud because most automation systems, people are upgrading software patches, those sorts of things, and doing them one at a time in their automation systems. In the cloud, there's no way you can afford to do that. You have fleet management tools where you're allowed to look at and administer patches, take commission, one-click commission, new edge devices, for instance, directly from the cloud. That's something we need to get to in automation as we look at more and more edge-type devices coming into play in addition to the critical control devices. Multi-tenant software, writing software, realizing there may be multiple clients using the same piece of software, but that their data needs to be securely and independently segmented from each other, with the idea that you end up with one instance to take care of. And then, of course, or platform as a service. And this is the idea where the cloud itself is not only kind of the operating system for you, but the software pieces and tools from an infrastructure point of view, databases, analytics tools, visualization, all of those are built into the cloud and accessible to you, and you focus all of your effort on writing the specific domain application that you need to have. So with all these new technologies coming from cloud, how can we take advantage of those in our world at the edge and in automation? And for that, I have another friend and colleague, Mr. Claudio Fayad, who's going to come talk to you about that.
Thank you, Peter. Thank you. My name is Claudio Fayad. I'm the Vice President of Technology for Process Systems and Solutions, responsible for the DeltaV and DeltaV SIS development, and it's an absolute pleasure to be here. So Peter's talking about the cloud, and there's no way that we can talk about the future being boundless automation without talking about the edge. At some point, the edge was putting compute power close to sensors, which is great. And another person said, well, the edge is not a place. The edge is a technology. The edge is the extension of the cloud. The edge is the opposite of the cloud. Now, what actually gets me really excited about the edge is that it offers us a different way to talk about automation. It's not the opposite of what we're doing today. It's actually built on what we have been doing all these years and allowing us new ways to deploy automation. It leverages the cloud technology, like Peter mentioned, containers, Kubernetes, fleet management, but more important, it leverages the OT technology that has been developed through the last 30, 40 years. It also allows us to deploy software in a different way, and we're going to talk about that, which creates a lot of benefits, refines the communication architecture in a much more flexible architecture. It's data-centric, which is very important, and is secure by design. Instead of being securing the perimeters of the networks, we're going to secure every single node. But more important, the edge is where IT and OT come together to collaborate, to innovate. The edge is where we break all the silos and create value and innovation. So I'm going to go through each one of those. Peter already mentioned the cloud technologies. So I'm going to jump on the current OT infrastructure. So the edge combines those new technologies on the OT protocols that we have created over time. HART, Foundation Fieldbus, Profibus, OPC UA. That's what enabled that connectivity in the first place. If we take the edge as putting compute power close to the sensors, I mean, we have been doing that. That's the controllers from DeltaV. That's our EIOCs. That's our SIOC. Those are our RTUs, our PLCs, our reliability equipment. Nothing but putting compute power as close as possible to the sensors. And then on top of that, running workloads. Of course, the technologies that we use to do that and create that cohesive software platform were different. Big installations, then virtual machines, now looking into containers. So the portfolio that Emerson and AspenTech have put together over the years is nothing but the infrastructure of the modern edge. Now, when we look at converting this, expanding this to a modern architecture, the first thing we have to look at is how we're going to deploy the workloads, the software workloads. And it's actually done in two steps. The first one is the infrastructure. What would be the ideal infrastructure for a modern edge? You're looking at the hyper-converged infrastructure where no longer virtual machines and servers, you have a collection of hardware that is now running under one single OS that makes all those servers look like one single compute power. It all acts as one happy environment. All the storage associated with those servers, they become a single storage environment, a software-defined storage. And all the networking, the switches connected to those servers also become a single network that you can shape and change as you need through software. So no longer if I want this network, I need to think about the architecture of switches and devices to build that network. It's a software configuration, which gives all of us a lot more flexibility. We have actually just released the hyperconverged infrastructure for DeltaV. We released it about a month ago, and is a key part of our new DeltaV version 15. When we put that software-defined infrastructure, the next step is running the workloads. So you create now a software-defined automation environment, and you create workloads. The workloads, in part, are the software we have today, but in part is also a change. You look at the devices, Laura was talking about how we're going to have a lot more devices connected. That data is then aggregated, and it works in there as a container that represents the digital twin of the field device. And then that digital twin, or that data from that device, is then connected to different functionality. The functionality that we have on a controller today, a PID function block, a cascade loop, they're all going to be executed as independent containers inside that infrastructure. And then the data will go to HMI functions, to alarm functions, historian functions, all of that connected and working inside that common infrastructure. The benefits in there are huge. We can scale as we want, putting those functionalities in there. It's going to be not only redundant, as we have redundant controllers, but it's going to be redundant and fault tolerant. We have redundant control. If one, for some reason, stops working, I can automatically start it again and rebuild the redundancy on the fly. I can now upgrade each container individually. I don't need to be upgrading a massive amount of controllers or workloads. It improves performance and does an efficient data distribution, and that's key. I mean, if devices will increase an order of magnitude, the data generated by those devices is going to increase another order of magnitude. And when we look at all those devices and all that data, people are reluctant to connect those new devices to a DCS. Because the architecture today means if I connect to the DCS, even if all I want to do is visualize or optimize the plant, I have to send that data through the controllers, which becomes more expensive. In an architecture like that, we're not only combining, but on a DCS like DeltaV, it means the data will go wherever it needs to go with any extra inefficiency or path. So that frees all the data, making those data pathways more effective. So once we look at the workloads, that's the first step. The next thing the edge gives us is a flexible communication environment. We're all used to the Purdue model. Data starts on level 1, has to go to level 2, then level 3, then by that time it's 4 firewalls later. I mean, it keeps going. If you go on a more modern edge communication infrastructure, you can still do the same. If you want to do that, you can still have your data through your OT infrastructure, to your IT infrastructure, which happens to be shrinking today. People want that to be more streamlined. So the edge will allow you to do that, but it also allows, like Laura mentioned, it allows us to build controllers and software-defined controllers that will send data straight to the cloud. If you need things that cannot afford latency at all, we're going to put the workloads and the communication on-prem close to the sensors. Things that can afford more latency can be on a cheaper, a more effective data center somewhere, or even in the cloud. By changing that communication is where we create the boundless automation by completely breaking the horizontal silos between the different functions, as well as the vertical silos created by the Purdue model. It's not about OT protocols versus IT protocols. It's about putting them all together, putting the right protocol to do the right job. The thing is flexibility, allowing you to have all that data and move it together with its context to where it needs to be consumed. It also allows the workloads to be executed wherever you want them, on-prem, close to the sensors, inside the OT infrastructure, inside the cloud. It increases data accessibility. That kind of brings us to the next topic. I have heard it many times. I'm sure you all have as well. The horror stories about people bringing all that data in the beginning of their digital transformation, building those huge data lakes, and those become what they're now calling data swamps. Think about terabytes, hundreds of terabytes, petabytes, and all that of data that you don't know what it means. And now that they're together, you're going to try to figure it out. I don't think we have found anyone that can do that yet. Because it's not enough that you put the data together and contextualize it. The contextualization has to happen in the source as it's being generated, and then move along with the data so anyone can actually benefit from that data. So that's what we call data democratization. So just to give you an example on that, right? If we look at any asset on the plant, a pump, a heat exchanger, there are multiple dimensions of that equipment. You have real-time data, process data. Normally comes along with the historical data, comes along with alarm and events. Maybe it's in a different database. Now you have reliability data, not only stored in a different place using different technology, but owned by different people. Then you have production data, and you may have many other data like specs, and you don't even know how that's all related together. Now, compare that with the other picture where you have a unified data model, where not only you have the data of all the different aspects, but you also have the lines in there representing the relationship between that data. So I can easily see all the data that belongs to my pump, all the data that belongs to a moment in time on my process. That's what we mean by contextualized data. And by combining that with a unified data model, we build a very strong knowledge base. Now, why would we do that? Let me share an example. Imagine that a plant on a given day, the yield was less than expected. The plant manager said, well, it was not 100%, it was 95%, let me call my process engineer. And he simply asks, what happened to my plant today? At that moment, you're going to have a very, very busy process engineer. He's going to be calling 5, 10 different people. What happened today? What alarms we had? Oh, we had alarms. What happened before the alarm? What happened after? How is the reliability? And if that issue spans across multiple units, you can talk about 20, 25. He's going to be lucky if 2 days later, a week later, he has the final root cause analysis for that issue. By that time, I mean, everything is gone. Now, contrast that with the other model, where the data is there, the data is connected, is contextualized. It doesn't belong to different people. You don't have to call different people. You can make that data available to a single person because it's all contextualized. That person can manually answer the question, or you can feed that into an artificial intelligence machine learning model that will basically answer the question for you. The yield today was 95%. There were 3 alarms, all related to this pump. The unexpected shutdown was mostly caused by a combination of wear and tear and an inclement weather, because now we have all that context in place. Again, it can be created by one person that was able to put it all together by querying the database with all the connections, or automatically through an AI system. And that's what we're all pursuing. And we can only do that if all that data is generated and is stored with a data model that anyone can understand. So as we talk about software workloads, as we talk about flat networks, as we talk about moving data everywhere, the next big question that Peter already talked about is security. So it's not enough anymore in that model where everything is connected and talking to each other to have perimeter defense. We are used to protect, like we protect our houses, and from that moment on, everything inside we trust. Well, when one of those things are compromised, now you have a big issue. And with more connectivity comes more doors for that attack. So what you need to do is actually secure from the inside, secure by design. We have already started that 4 years ago when we certified DeltaV as an ISA secure SSA, which that means that every line of code in DeltaV is developed by people that have been certified on secure development lifecycle, that have been validated, analyzed for vulnerability. And that's how you get that certification. And we have to expand that across all the systems and solutions we have. Peter talked about containers. They're not just right in terms of size, they also offer a paradigm where now each software workload lives in their own sandbox. If it gets compromised by any reason, it doesn't spread. It doesn't infect the host. It doesn't infect the whole network. You shut it down, you start up a new, fresh version of that. And in the end, we get to that zero trust architecture. We have that containerized software that even if it gets infected, but more important, now you have to describe the expected behavior of the system. And only workloads that are expected to talk with another workload will be allowed to talk. If all of a sudden something shows up and start talking with the other components, they're just going to say, hey, I don't know you. The control plane, which regulates that, will not allow that communication. So that's how we prevent those zero-day attacks. So I know all this is kind of talking about the future and the boundless automation, but we're building the future today. Two products here that I want to highlight. One is the DeltaV Edge environment. So the DeltaV Edge environment, it starts that transformation from within DeltaV. We're going to keep DeltaV as it is, and we're going to connect the DeltaV network to that DeltaV Edge environment through a data diode. So at the first moment, you only have one-way communication. There's no way the data can come that. And we're going to replicate not only the DeltaV data, but the DeltaV configuration and context. So you're going to have an on-demand digital twin of DeltaV on that edge environment. And now all your data scientists, anyone you want, can go there, manipulate the data, play with the data, use the data, generate reports, insights, connect them to the cloud without actually touching the DeltaV control system. Package, on the other hand, is our solution on our PLCs. We have actually created a PLC that has two CPUs, has two sides. On one side, you do real-time control. You do motion control. You do interlocks, all the things the PLCs are good for. On the other side, inside the same hardware, you're going to have all the edge technologies, containers. You can load your own applications, optimization algorithms, connectivity, all of that allowing you to have the best of both worlds. With PLCs, when we automate machines one by one, you end up sometimes with an island of automation where everything is disconnected. Instead of putting a whole new layer to figure that out, we can do that with this dual nature of our PLCs. So my last slide, 30 years ago, it was a lot of marshalling, a lot of cable routing everywhere, hundreds of cabinets, I/O, controller, a big building. Every software would go on a specific server or hardware. Then you move to 2010, 2011, we introduced electronic marshalling with charms. At that point, we eliminated the marshalling cabinets. We changed the I/O cabinets to electronic marshalling. We reduced the building. We reduced energy consumption. We reduced air conditioning. We also introduced virtualization, where we moved away from all those independent servers to a single server or two servers for redundancy. You jump to 2018, we introduced distributed charms. With that, we eliminated the whole I/O cabinet. And now when we look at this architecture and what it will bring, if we use all of it, first, we're going to simplify the way we connect all those devices through APL, getting all of them connected so they can all be used where they need. A unified software-defined infrastructure running on a hyper-converged equipment that will get all that data and put it on the right place. And then leveraging the edge and the cloud that Peter presented, we're actually going to allow you to not have to operate the plant for a specific physical location. You can still do that if you want, but you're going to be able to operate it from the plant floor. You're going to be able to operate it from the outside, whatever your security policies and your operation allows you to do. So when we look at the future, we're breaking the silos, but not having multiple systems, but having an enterprise operations platform that is software-defined, data-centric, and a flexible enterprise operation. So with that, I'll call Peter back to stage.
Okay, thank you very much, Claudio. Now, so the actual goal that we've talked about for a long time with the Plant Web Digital Ecosystem is still the same goal. It's still that same goal of getting the data, running it through the right software application that has the codified knowledge to derive action that delivers results. Here, as we talk about the boundless automation architecture, we're talking about a software architecture to make that a lot easier to do and a lot easier to write the applications to deploy on that software architecture to actually let you pull that off.